slide down it.
Yeah.
Give himself some acceleration. I'm just curious though, 3 stories, let's call that about 15 meters. Just saying. If you accelerate 2.23 meters per second squared for 15 meters, how hard will you hit the ground still? With what velocity will you hit the ground, I should say? So let's see.
Well, no, because right before he hits the ground, he would just grab onto the rope and have it stop and snap, and then.
Or he'd just let go. But then he'd accelerate even more because
That's
of
the thing,
gravity.
He would hold on more and he'd snap right to the ground to take some of the acceleration.
No, it actually wouldn't.
Really?
Well, gravity is going to. He's accelerating, he's gotten up to a certain velocity, and then gravity is greater than whatever acceleration he's doing down the rope, and that's going to start pulling him faster. So his best move is just to keep going until he hits. Unless he stops and the rope takes a second to snap. But let's assume it'll snap instantly. And just say he rolls with it. You're not wrong that if the rope takes a second to snap, it could bleed a little bit of that off. But let's just say he goes right into the ground. He's not even paying attention. This takes too much concentration. So let's go back to this equation. Now, he's sitting on the ledge of his window, okay? The total distance he's going to travel is 15 meters. Call his starting position 0. He started sitting on the ledge there. Let's say his initial velocity was 0. So all we have to... Oh, this won't work. I'm sorry. We don't have time, do we? I pulled out the wrong equation.
No.
Let's go back to this one. We have v squared equals v initial squared plus 2ax minus x initial. So his final velocity I'm curious about. His initial velocity is 0 meters per second squared. His acceleration is 2.23 meters per second squared. And his total distance is 15 meters. And so his velocity is just going to be the square root of 2 times 2.3 meters per second squared times 15 meters. I will get meters times meters makes meters squared over second squared, so I will get meters per second. What's the square root of 4.46 times 16? It's going to be 60 something, so I'm looking for around 8. 8.44 meters per second. So he'll hit the ground a little faster than the fastest, said that he'll hit the ground a little faster than a nationally ranked track athlete could probably run into a wall.
Ow.
Well, wait, I got 8.18.
8.18?
Yeah.
May I see? Yeah, that looks a little more accurate. Shall, I'm going to roll with Tyler's here. I see his steps. Okay, so that's 8.18. So still, that's very fast. That's basically you sprinting into a wall. But what's his alternative?
Getting caught.
Getting caught, sitting in jail?
Splat.
Well, yeah, I'm thinking splat's a good way. His alternative is, I'm just going to take this exact velocity equation, and we'll talk about how that's a shortcut later. And I'm just going to put in gravity instead of this acceleration
Oh, that's even worse.
times 15 meters. And tell me what this number is, 2.9.80 times 15. And then square root that.
Oh, 17.14.
17.14 meters per second.
Well, 17.115.
I'll take it. Okay, close enough. So that's twice as fast. So that's getting hit by a car in a residential zone that's going over a little over the speed limit.
Oh.
Noticeably over the speed limit, actually. So these are his choices if he drops.
I'd
But
take the
Broken
8.18
bones.
any day.
I'll take that, yeah. But he's got to accelerate down the rope. But you guys get the original idea. The rope has this much tension on it. It can only handle this much tension. So if you accelerate down the rope, it's the same thing, actually. You could lower something heavy on a rope, heavier than the rope in theory could handle. If you stopped, as long as you keep accelerating. What happens if he accelerates down the rope as fast as he can, and then because he's not concentrating or he doesn't know how to go any faster, he goes to a constant speed? What'll happen?
Little snap.
It'll snap. There's no difference in this perfect situation we're
Well,
describing.
he has to
He has to slide, he can't jump like that.
He could if he
Well,
kept
Rob, none of
moving
these
fast enough.
slide on
But-
sheets, so.
Eventually, you're gonna
Yeah.
have to slide.
We are pretending he's a particle. You're probably, I mean, it'd be very hard to avoid a point where your weight settled as you transfer.
Yeah, I
You're
don't
right.
pretend to
You
So
would
a
be
slide
pulling-
would be a
And
better
you
way
would
to
be
think of it.
pulling on it too.
Yeah. It'd be, well, you'd be pulling as you lowered. Your timing would really have to be perfect.
Would-
You'd have to
That's why
be, you'd have to be
you slide.
pushing yourself down from the moment you grabbed it. It'd be
Yeah.
kinda,
Like you were jumping out of a helicopter. So-
yeah. It'd be really hard to do. I don't see anyone really pulling this off, but it is an interesting exercise. I just wanted you guys to think about that point, that,
No petty thief is gonna be able to do that.
No.
Mr. Belvo, when I go
It
home
takes
tonight,
a
I'm gonna tell my parents you told me how to make an escape
Out of
after
prison?
a robbery.
that's great. I'll make sure they, thank you for telling them what a good influence I am. The bigger point of this that I want you guys to think about, okay, did the petty thief's mass change?
No.
No. Did his weight change?
Yes.
Yes.
Yeah.
Weight changes under all sorts of conditions. Your weight is changing all the time.
Celebration.
But your mass doesn't. So this is a good exercise for getting the difference. He changed his weight by accelerating towards the ground in the opposite direction of gravity. He lessened his weight. I just lost 30 pounds. Ask me how. I accelerated down a sheet. No change in mass whatsoever.
But I gained it back.
That's right. Regained it the moment I stopped and the sheet snapped. All right.
Yeah.
Tomorrow we'll do a demonstration. Thursday we'll review. Friday test. Tyler, go ahead and kill it.